So welcome to the lecture about gradient descent updater strategies. This is a very important lecture because choosing the correct gradient descent updater strategy might heavily influence your learning. So remember, in gradient descent we are testing one random value because that random value is generated by the random initialization of the weights, and from there you have to find the next step. So the next step you find, of course, by computing the first derivative of the cost function, and you go in direction of the steepest descent. But there are some catches. So let's start with gradient descent as it is. So in gradient descent you update the weights theta by subtracting a value from it. So the value which you are subtracting is this one. So let's have a look how this is computed. Again, it starts with a cost function j. The cost function j is of course dependent on theta, the weights, but also on the training data. So the training data I have exemplified here using a matrix X and a matrix Y. So this is basically the complete data set, and once this cost function is computed on the complete data set, we take the first derivative, we get the gradient, then we multiply by the learning rate, so the update will be smaller, and then we subtract from the actual value of theta t, and that gives us theta t plus 1. So that's how gradient descent works. So there's a variation. This is called stochastic gradient descent, and the only difference is that you are not computing the gradient on the complete matrix X and the complete matrix Y. You just take one training example. This is xi and yi. So once you have computed the gradient, you update already the parameters theta. So a variation of this is the so-called mini-batch gradient descent. So that's somehow in between. You don't use the complete data set, and you just don't use a single instance of your data. You just use a batch. So the batch size we have to define. Usually you take values between 32 and 1024 or so. And then you compute the gradient for that particular batch, and once this gradient has been computed, you update the parameter matrix theta. So now another way of doing this is called momentum. So in momentum the idea is that we take also an update of a past time step into consideration for computing the update of the current time step. So now we have here a variable called nu. So nu is computed from nu t minus 1, and usually we take a gamma of 0.9, and from this we basically subtract the actual gradient. Once we have computed nu t, we subtract nu t from theta t, and we get the updated theta t plus 1. So there's a variation of momentum. This is called Nesterov accelerated gradient, and the only addition here is that in the cost function we subtract this term here already from theta t. So in a visual way, this is like a ball rolling down the hill, and it's a smart ball. So whenever the slope starts to increase, the ball stops accelerating and brakes a bit. So ADAGRAD, which stands for adaptive gradient, tries to change the learning rate over time, and not only for the complete batch, it tries to change the learning rate for each individual example. So you see here, this formula is dependent on I, so I stands for the actual training example. So we see here that the learning rate eta is modified, and it's modified by this term here. So GTII is a matrix which contains information on the past gradients per training example, and taking this into account, it just reduces the learning rate. And note that there is a little term E, so that we avoid division by 0. This whole thing can not only be computed per example, but also using matrix-matrix multiplication, and therefore we can omit the I, because GT is a diagonal matrix. So don't worry if you don't understand this, so maybe you have to revisit the linear algebra basics, but anyway it's just a way to compute the whole math in just one go. So eta delta is only a variation of ADAGRAD, and the difference is that it doesn't use a matrix G, but it continuously computes the mean of the historic gradients. So there are many other variations of gradient descent updaters, and I recommend you to have a look at Sebastian's blog later, where everything is described really nicely. But the key take-home point here is that the gradient descent updater strategy is a very important knob you have to tune, and as usual, tuning a neural network is considered as black magic or trial and error, so you just have to try a couple of those. So let's actually have a look at Sebastian's blog. So Sebastian is this funny guy here, and you see here those are the trajectories of different learning curves using different gradient descent updater strategies. So it's pretty interesting because it's a very important hyperparameter you can tune. So we have covered most of those, but what I wanted to show you is two little figures here. So those two are really interesting. So you see here different trajectories in optimization space using different gradient descent updaters. So the red one here is stochastic gradient descent, and you see here in both problems it performs really poor and it even gets stuck. So maybe in the first image it won't get stuck, but it won't converge for ages, and in the second, this is a saddle point, it even gets stuck. And you can see here that, for example, adder delta is performing best among all of those. Okay, I think that's enough for now. I hope that you now understood that this is an important hyperparameter which you can tune, and that's basically it.